In the last video, we learned that 380,000 years after the Big Bang, which is still roughly 13.7 billion years ago, every point, I shouldn't say every point, every atom in space that was kind of at this roughly 3,000 Kelvin temperature was emitting this electromagnetic radiation. Since every point in space there were points in space, or there was points in the universe, that radiation is only just now reaching us. It has been traveling for 13.7 billion years. So when we look at radiation that's been traveling for that long, we can look in any direction and we'll see this uniform radiation. And that radiation has been redshifted into the microwave range from the higher frequencies that it was actually emitted at. Now, a question that might pop in your brain is, well, what happens if we wait a billion years? Because if we wait a billion years, if we have a billion 380,000 years after the beginning of the universe, this stuff won't just be atoms anymore. It will have started to condense into actual stars. We would not, the universe at this point at every point in space will no longer be this uniform. We'll actually start having condensation into stars. So if we go the universe, if we move forward a little bit, the universe will expand. Maybe I'll just draw half of it. Since it's expanded, it's obviously expanded much more. But now all of a sudden we actually have stars. These are no longer just uniform atoms spread through the universe. We actually have condensation into stars. And so if you look at what is being emitted from the points in space from which we're only now getting this cosmic background radiation, if we wait a billion years, what the light that we see from those points in space will not look like this uniform radiation. It'll start to look a little bit more like the more mature parts of the universe. We'll essentially be looking at the universe a billion years after the Big Bang, when stars have formed, other structures have formed. So the question is, in a billion years, will this cosmic microwave background radiation disappear? And I'm using the billion just because that's, just to arbitrarily use a number. But will it eventually disappear? And there's kind of, the answer to that is yes and no. So to think about it, it is true that this point in space will mature. It will mature in a billion years. It will no longer be this uniform, this uniform haze of hot hydrogen atoms. But what you have to think about is there were further points in the universe. There were further points in the universe. At that same time, there were further points that were also emitting this radiation, and the original photons from those original points still haven't gotten to us. So from those further out points, right now the observable universe is, we can only see electromagnetic radiation that's been traveling for 13.7 billion years. In another billion years, the universe will be a billion years older, and then there will be radiation that has been traveling for 14.7 billion years. And so we will start to observe that. And we'll start to observe that radiation from the same time period in the universe. It'll just be from further out. Now, what I want to make clear is that since those points were even further out, where that radiation was emitted, the stuff that we'll see in a billion years, it will be even more redshifted. Even more redshifted. So at that point, the cosmic background radiation we see will have longer wavelengths than the radio spectrum. It will be redder, and I should say redder because we're already more. Would redder have two D's? I've never written redder. Well, it would be more red than the microwave radiation. And of course, that's a funny thing because microwave radiation is already more red than actual visible red light. It has a longer wavelength. Now, this will keep happening, and I don't know at what, it'll keep happening. We'll keep getting radiation as we go further and further into the future. We'll keep getting radiation from further out points in space, and it'll get more and more redshifted. The actual wavelengths of that electromagnetic light will be bigger and bigger and bigger, until we really aren't able to even see it as electromagnetic light, because it'll be redshifted to infinity. It'll have an infinite wavelength. And to make that point clear, I want to show you that there'll even be points, at some point, there'll be kind of a threshold where we can't even get radiation from further out. And let me show you, let me draw a diagram of that. So let's say that this is the universe. Let's say that this is the universe 13.7 billion years ago, right when that radiation, what we now see as cosmic microwave background radiation, right when it started to be emitted. And let's say that this is the point in the universe where we are now. So this is us. Let's say let's say that this is the point in the universe that where we now observe the background radiation, or this is one of the points. We obviously could form a circle around us. It could be any of these points over here, where we only we that where the photons, the electromagnetic radiation that were emitted from this point 380,000 years after the beginning of the universe is only just now reaching us. So this is the point in the universe from which we are observing the cosmic background radiation. And let me be very clear. That point in the universe has now matured into things that look, into stars and galaxies and planets. And if they were to look at our point in space, they are also going to see cosmic background radiation from us. It's not like this is some type of permanently old place. It's just the light we're getting from them right now is old light, light that point in space emitted way before it was able to mature into actual structures. So this is the point in space from which we are receiving cosmic background radiation right now. I don't want to write all that. It'll take me forever. Now, let's take another point in space that's whatever this distance is. It's actually estimated to be about, now it's estimated to be about 46 billion light years. At that time, when things were just beginning to be emitted, this was only about 36 million light years. So this was and this is a very rough estimate. I shouldn't even write it down because that's really based on how fast we assume the universe is expanding and all of that type of thing. But it was just a lot smaller than 46 billion light years. Now let's go that same distance again from this point in space. So once again, let me make it clear. This is 380,000 years ago. 380,000 years ago. Now let's fast forward. Sorry, not 380,000 years ago. 380,000 years after the Big Bang. After the Big Bang, which is approximately, it's still 13.7 billion years ago. So that's then. Now let's look at now. And now I'll just draw it a little bit bigger. It's actually going to be much, much bigger now. Now if we do it a little bit bigger, so when I draw it like this is where we are now. This point in space is this point in space from which we are only now receiving that cosmic background radiation is over here. And then this other point in space is going to be over here. And we saw in the video on the actual size of the observable universe, not just what it appears to be based on how long the light's been traveling. This is now on the order of 46 or 47 billion light years. 46 billion light years. And so this distance is also going to be 46 billion light years. 46 billion light years. Now, every point in space back then was emitting this radiation. We have this uniform radiation. It was just hydrogen atoms everywhere, these hot hydrogen atoms. Now, we are only, maybe I should just do it in the color of the radiation. So this guy's receiving, I'm just showing it's coming from this guy. We're only now, 13.7 billion years in the future, receiving photons from this guy. Only now are we receiving it. And frankly, this green guy only now is going to be receiving photons. When he looks at the points in space, or the things that he thinks are the point in space out there, he will see that uniform radiation. And likewise, this guy over here will only now be receiving photons from the point in space for where we are now. He'll see the universe where we are now as it was 380,000 years after the Big Bang. And same thing from that point in space. The photons will only just now reach. Now let's think about it. It took this guy's photons, let me make it clear. It took him 13.7 billion years to reach this point over here, which is now 46 billion light years away from us. And the universe continues to expand. It's depending on if the universe expands fast enough, there's no way that photon that got to this guy will eventually get to this. The universe is expanding faster that the light can never even catch up to us, and this light will never, ever, ever get to us. And so there is some threshold, some distance from which we will never get light during this time period, or actually from which we will never, ever get any electromagnetic radiation. So the simple answer is the cosmic background radiation from this or the cosmic background radiation from this point, yes, it will start to mature. It won't be as uniform if we go fast forward 400 million years or a billion years, but we will get uniform radiation from further out, but it'll be even more redshifted. And the further forward we get into the future, the background radiation we get will be from further and further out, and it will be more and more and more redshifted until some point where it's going to be so redshifted that we won't even observe it as electromagnetic radiation. And there's some threshold where we won't even observe anything anymore because beyond that, the light wasn't able to actually get to us.